This video is an introduction to contact angle measurements that we can make here at the Materials Characterization Lab, part of the Penn State Materials Research Institute. When measuring the contact angle, we're investigating the balance of forces acting at the interfaces. More specifically, we're looking at how the interfacial free energies are shaping that liquid drop on a solid surface. Thomas Young was the first to formally investigate this phenomenon in 1805. Followed by Anatase and Paul Dupree in 1869. The work resulted in the equation listed above, showing that the contact angle between a solid and a liquid is governed by the interfacial free energies between those three phases. This was a wonderful generalized relationship for surface energy, but as we can see, there are four terms in the equation. Measuring the contact angle removes one of those, but there are still three terms that must be accounted for. This means that some prior knowledge of the system is required to obtain surface energy measurements with this method. So, if we want to get an idea of the surface energy of a solid, it's going to take more work than just dropping a liquid onto a solid and taking a picture of it. What I just described could be very useful, however, for qualitative measurements, where typical contact angles are known for a certain liquid on a certain solid that has undergone a polishing or been etched or some other treatment. Let's use the example of plasma-treated graphene. If you know the typical contact angle for water on plasma-treated graphene, variations in the measured contact angle could help to identify when something has gone wrong in the synthesis or treatment steps. If the goal is to approximate surface energy, however, a model representing the interfacial system must be used. The simplest model for this application is the Ziesmann model, which applies to surfaces that do not contain any polar contributions to the solid-liquid interface. A good example of a system that falls into this category are hydrocarbons on high-density polyethylene, shown on the table on right. If you end up having polar contributions on your surface, you have to use a model like Owens, Wendt, Fox, or there are many others. The Ziesmann model states that surface energy of a solid is equal to the surface tension of the liquid that is just barely wetting the surface completely, corresponding to a contact angle of 0. For this example, we stop witnessing complete wetting happening at 23.8 millinewtons per meter, which is the value for n decane, putting the surface energy somewhere between 21.3 for octane and 23.8 millinewtons per meter for decane. For a more accurate surface energy value, we can plot the line corresponding to surface tension of the liquid against the cosine of the contact angle. Then, we can extrapolate the linear section of the plot to find the surface tension value where the cosine of the contact angle is equal to 1. This is all well and good, but what happens when we don't know the surface tension values of the liquids used for the measurements? In this case, we can use a technique called pendant drop and sessile drop to gain more information about the surface tension. Both methods analyze the shape of the drop, either as it hangs from the syringe tip or as it sits on a solid surface. On the bottom of the screen is a diagram paired with the actual images from our instrument. We have the ability to feed back off of the volume calculated in the live image to keep a constant drop volume. That can be very helpful. And the software that controls the instrument is also used to analyze the data, using image processing algorithms to return the results. Other software, such as ImageJ, could also be used to extract the shape of the drop, and in the case of the sessile drop, utilities such as Wolfram's configuration of a sessile drop can be used to fit the data. I won't go into the details, but using a careful combination of these techniques, we're able to estimate the surface tension of our liquids, which can then be used to estimate the surface energy of our solid. The instrument used to make these measurements here at the MCL is the Reinhardt Model 590. It's called a goniometer tensiometer because it can measure both the contact angle and drop shape, giving information about surface energy and surface tension respectively. Some of the capabilities of the Reinhardt 590 include being able to tilt the stage to attempt to deconvolute the effect of gravities and other surface tension components. Our environmental control attachment allows us to raise the temperature up to a stable 250 degrees Celsius and operate from a low vacuum up to 0.6 atmospheres. An inverted needle and quartz cell attachment allow for liquid-liquid studies, inverted sessile drop, and captive drop experiments. The Reinhardt 590 also allows us to take multiple data acquisitions spread out by a specified time interval, allowing for time-dependent studies to be carried out. As for considerations and limitations, the largest limitation is that the smallest drop size we can achieve is right around 1 millimeter. We can't go much smaller than that. The other thing to consider is that we're not directly measuring the surface energy. Surface roughness, chemistry, The heterogeneity of the surface and the choice of liquid will all have an effect on the contact angle, so it's important to choose a model that best fits your material system. On behalf of the Penn State Materials Characterization Lab, thank you, and we hope to see you in the lab soon.